I was just telling James that I think this is a good lesson that we're about to have because nomenclature is a big topic. And depending on how much time you've invested so far, it's like a hill to climb and it just takes time. You have to keep climbing. And some people climb faster than others, but everybody has to get over that hill to stay in the class, like to understand chemistry. And I was just telling James that, so last week was ionic compounds and this week is covalent things. And we've already learned how to name elements. You'd be surprised. People are going to struggle with naming elements this week because that's just how it works. It always happens that way. Anyway, so this lesson just talks about when you walk up to something, the first thing you need to do is classify. And so I'm hoping that since you've already spent some time in nomenclature, that this will help clarify some things. So I hope that it is helpful. Nomenclature is just work. And then typically the students, well, it's work for everybody. So it's frustrating for everybody probably. But honestly, the students who invest the time start to see the puzzle and start to find some joy and some pleasure in solving things. And the students who have maybe sat through classes and just listened and got enough to get by, they don't like nomenclature because it requires effort that they aren't used to committing. And I don't know where all of you fit on that whole spectrum because, we all start somewhere, which is fine. And so if you were the bright, lazy student in high school, that's okay. You're still welcome here. And hopefully you'll learn how to work and that will serve you well in the future. And if you're the student that just does the work and has already found the game in it, that's awesome. We're finally getting to chemistry. We've talked about how to measure things, how to count sig figs, how to do unit conversions, and those are super important, how to calculate a standard deviation if there's replicates. But now we're going to start talking a little bit more about what is the stuff that is matter. And matter can be classified. And so this is a really important way to classify that hopefully will help you as you approach nomenclature. And there's some assignments. And the assignments this week, for example, there's a lab worth 20 points that is just naming things. I don't know if you heard this part, so I might be repeating myself. Just Googling does not help you, and it erodes your character. It is cheating. But doing the work and comparing with friends, and then if you have different answers, discussing who's right and why, and if you can't come up with the right answer, asking me, that is not cheating, that's learning. That is the hard work that is necessary to put the learning in your head. And so I suggest that you do that lab early, but don't turn it in. Compare with friends and ask questions if you have them. And I am happy to answer those questions because I want you to get full credit after you do the full learning. Does that make sense?
Yes.
Okay, so here we go. Classifying substances. What kind of substances matter? And sometimes we just talk about species. So I'm going to use these words. Substances is referring to matter. And sometimes we say species and they all mean the same thing. It just means a kind of stuff. It is super important and it will help you a lot, not just in nomenclature. So we're just going to start at the beginning. We learned that there's elements and that elements have names and symbols that represent them. Most elements are monatomic. And so sodium is a metal that exists atom next to atom next to atom in the solid and liquid phases. Iron is an element that exists atom by atom. Carbon, atom by atom. So one capital, no charge showing, that's an element. There are 7 diatomic elements that you need to memorize. It's a 7 starting at 7. And so you could say nitrogen, oxygen, fluorine, hydrogen, chlorine, bromine, and iodine. They start at element number 7, which is nitrogen, and they sort of make a 7 on the periodic table. Or you could memorize it with mnemonic, like horses need oats for clear brown eyes. Or a lot of times students prefer this one. Have no fear of cold beer. However you memorize them, though, you have to know them. You have to recognize that when you hear about iodine, it's I2. And then if you do this, have no fear of ice cold beer. Make sure you have chlorine, not carbon, and bromine, not boron. I've seen people do that wrong quite a few times. Okay, so there are 7 diatomic elements. And then there are some elements that are polyatomic, many atoms. And in our class, those ones are phosphorus, ozone, and sulfur. 4 has 4 letters, old has 3 letters, Superman has 8 letters, poor old Superman stands for phosphorus. RUS, there's no O there. Ozone is a different allotrope of oxygen. So O2 is oxygen, but O3 is a different form of that element. And we call those different forms allotropes. If you're ever on Jeopardy, you might need that word. And then Superman stands for sulfur, SULFUR, and spelling does count. So you need to know when you recognize an element and then just name it as an element. I know that doesn't sound tricky, but there might be a day when you run across something like this, and these are wrong names I have seen for this. Dichlorine is not right. Dichloride does not make it right either. Wrong, wrong. The correct name is just the element. It's chlorine. Why is this important? Well, it's important for getting the nomenclature points. But also, why do we need to learn how to speak? We're in a language class. We're learning how to speak in a language, which is science. When will you run into it? When will it affect the actual chemistry part of the science? If you're asked how many chlorine atoms are in this many grams of chlorine gas, the question is saying how many Cl atoms are in 32.4 grams of chlorine, Cl2. And you have to recognize that this 2 here means there's 2 atoms of chlorine in every unit, every molecule of that element. And so somewhere you're going to have to take care of that too. Because we're also looking at Avogadro's number and how to use the periodic table, I'm going to go ahead and work through this problem right now. Okay, so there's a couple roadmaps we could take. We could go from grams of chlorine. We have to do the first step this way, to moles of chlorine. And we do that using the periodic table, the number that's given for the weighted average, and then we double it because there's 2 chlorines in a molecule. And then we could go from moles of chlorine to Avogadro's number of chlorine molecules, and then to chlorine atoms. Or here, we could go from moles of chlorine to moles of chlorine atoms, and then use Avogadro's number to get to individual chlorine atoms. It is probable that most of you haven't seen the video this week that was posted today. And so if this doesn't make sense, don't even worry about it. I'm still going to walk through it, and then you'll have it in your notes, and it might help you later. For those of you that have had high school chemistry or Chem A, this should make sense. And so for you, it's review. Okay, to get from grams of chlorine to moles of chlorine, I'm going to use the molar mass given on the periodic table. To get from moles of chlorine, the molecule, to moles of chlorine, the atom, I just recognize in the formula there's a 2-to-1 ratio. And then to go from moles of chlorine to chlorine atoms from the group, like a dozen is 12, a mole is 6.022 times 10 to the 23. To the individual pieces, I'm going to use Avogadro's number. So there's one roadmap. I'm going to do it that way first. So there are two ways of interpreting this number on the periodic table, which is a weighted average of all the isotopes. One is to say it's that many grams per mole. If I had a large grouping called a mole, it would have this much mass. And the other is to say it's that many atomic mass units per atom. So right now I'm going to use this idea, but recognizing that chlorine has the molecule, the element, has 2 chlorines, I have to double that number. So I've converted from grams of chlorine using the molar mass, and now I'm at moles of chlorine. And now I'm going to use the formula to get to moles of the atom. 1 mole of chlorine has 2 moles of chlorine atoms. And now I can use Avogadro's number to get to how many individual atoms that is. If I had 2 dozen donuts, I'd have 24 donuts. If I had 2 moles of atoms, I'd have 2 times the number that means mole, 6.022 times 10 to the 23 atoms. Okay, so let me just make sure things are canceling properly. And details, the devil is in the details. They really matter. Chlorine, like we find it on the periodic table, does not exist in nature. It's unstable. But chlorine, the molecule, does exist in nature. And chloride does exist in nature. So this is just a symbol that we find on the periodic table that represents a kind of atom that is not stable. But that atom can exist as an element. It happens to group together with another chlorine to become stable, or can gain an electron and become an ion and then participate in ionic bonding. When it is sharing electrons or gaining electrons, it's becoming stable in a way because it's isoelectronic with argon, the nearest noble gas. It doesn't become argon. It just has the same electrons and the same arrangement of electrons as argon, and that's stable. So I'm noticing here when I cancel grams of chlorine, Cl2, that 2 matters. That has to cancel, including the 2. And then if I have 2 chlorine atoms together, they're going to have this much mass, 70.9 grams in the group we call a mole. So now I have moles of the molecule cancel. And this step here is just recognizing that 1 mole of chlorine, the element, which is 2 chlorines stuck together, is equal to 2 moles of individual chlorines. So 1 mole of bikes has 2 moles of wheels, kind of that idea. Okay, so now moles of chlorine atoms, cancel moles of chlorine atoms. And then this number here is called Avogadro's number, and it's the number of pieces in a group that allow us to use a molar mass twice, or an atomic mass twice. So you did an activity where you took chlorine, which is element 17, and you added protons and neutrons and electrons, and you came up with some stable isotopes. There are 2 stable isotopes of chlorine. They're 35 and 37. And then there's a relative abundance of these, and it turns out chlorine 35 is just more typical. And when you have a large mixture of those, that would be the isotomic ratio that comes up to be the average. And so we take the weighted averages and we've come up with this number, 35.45, that represents 1 atom. But if you have 2 atoms stuck together, they're going to have twice as much mass. And then Avogadro said, well, we have this number that gives us the atomic mass units for 1 atom. What if we found a grouping number so that we could weigh a group and use that number again? And the grouping number that gives us grams to moles, the group called a mole, happens to be 6.022 times 10 to the 23. So that number came from this idea of, how can we use this number again, but on a balance? Because we can actually weigh things. We could never count atoms, they're too small, but we can weigh them. And so that's where that special grouping number came up. And the group number is 6.022, that's to 4 sig figs, times 10 to the 23, that's a lot of zeros. I started with 3 sig figs. This mass here, actually I need a 4 sig figs. This is unlimited because it's a ratio about the number of pieces in the unit. And then this number is good to 4 sig figs. Avogadro's number is known to more sig figs, but you don't need it for a class. 4 will always be plenty. So 3 is the limiting. 5.50, oops, that didn't work. 5.50 is 3 sig figs times 10 to the 22. Don't forget the exponent. And then the units need to be complete. Atoms, what kind of atoms? Chlorine atoms. Questions?
Sue, I have a question.
Yeah.
Why is it 10 to the 22 and not 23rd?
Probably because when I divided by 70, it moved the decimal over. Like 30 divided by 70 is like a half.
Mm-hmm. But then you multiply that by 2 moles and then by 6.
Did I forget to do that? Let me double check. 32.4 divide by 70.90 times 2 times 6.022 times 10 to the 23. Oh, you're right. I forgot something there. Good catch. Thank you.
Yep.
Yeah, I don't know what I did there. Okay, other questions? So when you're asked, I'm gonna clear my board because it's super messy, unless you tell me not to. When you're asked how many chlorine atoms in this many grams of chlorine, if you don't recognize that chlorine is a diatomic element, you're gonna get the answer wrong. And even if you got the answer right, because in this case, the 2's cancel out, it would still be wrong because the process is wrong, the thinking is wrong. The other way to do that, I did say I would go through, is I could go from 32.4 grams of chlorine. The next step has to be moles of chlorine. There's no other next step. But then I could go to molecules of chlorine. So use Avogadro's number earlier. And then get to atoms of chlorine. So I'm going to do it this time. And to get to atoms from the molecules, I'm going to have to use the formula. That's where I use that 2-to-1 ratio. Grams of the molecule, oops, it's being sloppy, cancel. The group of the molecule cancels. The individual molecules cancel to get us to atoms. Okay,
is there a preference that you have over which one we should be kind of getting accustomed to?
I'm sorry, say it again.
Is there a preference for which one we should be working with?
Nope.
No. Okay.
My personal preference is to go from moles to molecules before I go to atoms. Mm-hmm. But if you went from grams to moles of molecule to moles of atom to atoms, which is the way I did it first, it's fine. The last 2 steps could happen in either order and both be correct. I prefer the one I just did.
Okay, thank you.
But, you know, do enough of them that you have your preference. Yeah, as long as you're using this correct thinking incorrect in an order that makes sense, you're fine. Okay, so the moral of the story is you have to recognize that chlorine is a diatomic element. Here's another situation that's coming, it's just around the corner, coming up in a week or two, that you have to recognize the diatomic elements are two atoms that are covalently bound. This one says, write the balanced equation for the reaction of hydrogen. Horses need oats, have no fear, hydrogen, and nitrogen to form ammonia. Okay, so hydrogen plus nitrogen make ammonia. And what we're doing now is called balancing equations. And it leads us to something called stoichiometry, which is making predictions, answering questions based on balanced equations. That is a big part of our class. So I recognize here I have one nitrogen, and here I have two. I'm gonna have to double that. Now I have two nitrogens, the before on the reactant side of the arrow and on the after side. And now I have two ammonia units, and each ammonia unit has 3 hydrogens. So on this side, I have 6 hydrogens. I need to have 6 hydrogens on that side. And so there's a process that we're going to learn. I don't believe it's next week. I think it's the week after, which is balancing equations. And if you just wrote hydrogen, so what I'm doing now is wrong. Hydrogen plus nitrogen make ammonia. And you went, well, 1 nitrogen here, 1 nitrogen there, we're good. Put a 3 here, and you reported that as your answer, it would be wrong. Why? Because hydrogen and nitrogen are diatomic elements, and they have to be represented that way if we're talking about these elemental gases. Okay, so you have to know the 7 diatomic and the 3 polyatomic elements. And how do you know it's an element? Only 1 capital, no charge showing. Compounds have more than 1 capital with no charge showing. And there's 2 kinds of compounds. There are ionic compounds, are made from cations plus anions in a ratio where they add to 0. And so if our cation was sodium ion and our anion was sulfide, to get that to add to 0, we would need 2 sodium ions. And in the formula, we would write it this way. The 2 subscript to the right of sodium is referring to this ratio of 2 to 1. We don't write the 1, it's implied. So for ionic compounds, even though this compound is made from a cation, 2 cations and an anion combined to make something neutral, so the lowest whole number ratio is 2 to 1, we don't show the charges in the compound. More than 1 capital, no charge showing, that's a compound. Why is it ionic? Because it started with sodium, and sodium's a metal, and metals make cations. The only ionic compound that isn't going to have any metal in it is ammonium. So let's say we had ammonium and phosphate. We're going to need 3 ammonium ions to balance that -3 phosphate charge. Because it's polyatomic, I'm going to put it in a group with parentheses. And so this 3 here is subscript, but outside the parentheses to say 3 of that whole chunk of charge. And then phosphate is PO43 minus, but we don't show the 3 minus charge because we're in an ionic compound. When cations and anions are together, they hide their charges. They're still present, we just don't write them. Okay, so here we have an ionic compound that has no metals in it. So cations plus anions often means metal and non-metal, and the metal will always be stated first. But ammonium behaves like an alkali metal ion. Pretend ammonium is like sodium ion's sister or brother. So there are ionic compounds, more than 1 capital, no charge showing, and there are covalent compounds. Covalent compounds are stable by sharing electrons. They don't gain or lose electrons, they share to be isoelectronic with something stable. So here we have carbon dioxide. How do I know that's a covalent compound? Well, it's got more than one capital, no charge showing, and this is not a metal or ammonium. Here we have carbonate. Is that a covalent compound? No. More than one capital, but there's a charge showing. Here we have something that has carbonate in it, looks like. This is a covalent compound. More than one capital, no charge showing, and that is not a cation. Because even though a hydrogen ion hangs out in group 1, it is a nonmetal. All nonmetals sticking together by sharing electrons. That's covalent. So for covalent compounds in a couple weeks, we're going to learn, it might actually be in Chem 3B. We're going to learn how to make something called a Lewis structure to show where all the valence electrons are and how electrons are being shared. We can only do that for things that are sharing electrons. We can only do that for covalent species. So we need to recognize compounds, more than one capital, no charge showing, and we're going to focus on, is that ionic? Use the rules we learned last week for naming things. Or is it covalent? Use the rules we're going to learn this week. Questions? Okay, so we do name ionic and covalent things differently, and they behave differently. So why is this important? Well, we want to know how to name something because that's what we're doing this week. It's worth a lot of points. It's learning the language of the science, chemistry. But we also want to understand how things behave. And in general chemistry, we really focus on aqueous things dissolved in water. So if something is ionic, it's going to behave like our example here. So our example is sodium chloride. Super familiar. It's called a salt. It's not the only salt, but it's the table salt that we put on food. So things that are ionic are made from ions that are charged particles that are stuck together. Sodium ion and chloride ion are both stable and opposites attract. They stick together, but they don't stick together in a 1-to-1 ratio. I'm sorry, they do stick together in a 1-to-1 ratio, but they don't stick together just 1 and 1. That's a group. So we don't call that a molecule. What they do is they stick together in something called a crystalline lattice, which is a 3-dimensional repeating pattern. And so that's represented here with cations and anions. So every green sphere is a sodium ion, and every, honestly, I don't know which one's chloride. I'm gonna say every purple one is chloride, and they stick together. But if I had a sodium ion here, it would have 1, 2, 3, 4, and then a chloride in front and a chloride in back. It would be touching 6 chloride ions in a regular repeating structure that makes something that is crystalline. When something that is ionic dissolves in water, it dissociates into the ions that it's made of. And dissociate is a fancy word that just means breaks back into ions. And the positively charged ions, like sodium, get surrounded by the negatively charged end of water. So water is a molecule that has sort of a partial positive and a partial, oops, wrong way. Partial positive and a partial negative end. Or I could draw something called a dipole moment. And if you've had physics or calculus, you'll recognize some of these symbols. This little symbol here is meant to be a lowercase Greek d, that is a delta, and delta in calculus means partial. And then, so we have a partial negative end. That's the end that has oxygens, and a partial positive end is the end that has hydrogens. And in physics, we would represent that this way. We would have the partial positive end have the plus side of the dipole moment, and the partial negative end would have the arrow side of the dipole moment. If that doesn't make sense at this time, don't even worry. I'm just trying to tie into maybe some other things that you know from different classes, like physics and math. But if you don't know that, maybe you know this. Probably in high school science, maybe biology, they talked about water is the universal solvent. The reason it is such a good solvent that things dissolve in water is because water is very polar. And so that's that same idea. Water is polar. What does that mean? It has two poles, one that's negative, one that's positive. The negative pole is going to be attracted, the negative pole is going to be attracted to cations. And that's why all the little red oxygens here are facing toward the sodium ion, because oxygen is red in this kind of model. And then hydrogen is blue in this kind of model. And for the chloride ion, the negative ion has the positive end of waters pointing toward it. So ionic compounds, if they dissolve, that means it goes into water and I can't see it anymore. It's soluble. They dissociate, which means break into ions. That's super important. That means that we have electrolytes in water, and we need electrolytes to live. So ions in water is an important idea in life and in science. Wow, I've been talking in paragraphs and I have no idea how much of that is sticking. Could anybody talk to me? It makes sense. You've heard it before. What did this mean? Sue,
I've heard it before, and primarily I remember in earth science, because we talk about how water is a universal solvent and how it kind of decays at pretty much everything in life. But it makes sense how the positive sodium will be attracted by the negative oxygen. Yeah, and then inversely with the chlorine. So,
oh, good. I'm really glad to hear that.
Yeah, I'm keeping up.
So that was in geology, you say?
In earth science, yes.
Okay.
Geology.
Anybody else? Questions or comments? It would really help me. Even if your comment is, no, Sue, that's good. Move on. Okay, I'm gonna move on. So why do we need to know if things are ionic or covalent? Is to understand how they behave in water. Why? Because in general chemistry, we do a lot of things in water. Oh, look, here's water. So here we have water as a solid, a liquid, and a gas. And I just mentioned that water is a pretty important molecule. Oh, that just reminded me. When you watch the video that was posted, be sure and look for the extra credit opportunity. It has to do with water, and it's in there. Okay, so water is a molecule. It's made of two hydrogens and an oxygen that are sharing electrons. And so this little wedge here is to say those two electrons are being shared between oxygen and hydrogen. And this little dotted line means this hydrogen and this oxygen are sharing a pair of electrons. So things that are sharing electrons, like they're connected. They don't just fall apart in water. And so it doesn't break into hydrogens and oxygens. Water is a discrete unit. And that is the big difference between molecular and ionic things. Molecules are discrete, meaning separate from other things, units. Why? Because they share electrons. So they're not going to fall apart into pieces. Things that are ionic break into the pieces that they were made from. Things that are covalent don't break into pieces. The molecule is the smallest piece. So if something is covalent, we refer to it as being a molecule. If something is ionic, we refer to it as being a formula unit. There are no ionic molecules. And formula unit means this is the unit, the lowest whole number ratio of cations to anions. And ratio just means that it's a one-to-one thing. For every one of these, there's one of those. So the unit is given a formula. The unit is given a formula, and the formula is the lowest whole number ratio of cations to anions. And so we refer to this idea, NaCl, as the formula unit, which is the unit we use for the formula. Are we ever going to have 1 sodium and 1 chloride? Never. We're always going to have 1,000 sodiums and 1,000 chlorides. The smallest piece of salt that you can shake from a shaker is 1,000,000 sodium ions and 1,000,000 chloride ions. But if it's covalent, you can actually get just a discrete unit by itself. That's why covalent things tend to be, can be gaseous, because they can be independent of other particles. They're not a wide crystalline structure, although they can be when they're frozen. Again, I have no idea if any of this is making sense. It all makes sense to me, but it still feels a little jumbly. Anybody?
So does that mean that ionic is more fragile than covalent, basically?
Oh, the funny thing is, no. I mean, it sounds like it should be. If you hit it with a
Right.
hammer, yes, it's going to break into pieces. No, that ion-ion attraction is a super strong fundamental force. And
Okay.
so think of it this way. If you had something ionic like salt, can you put it in a pan on your oven and your stove and melt it?
No.
That opposites attract idea is so strong. There are 4 fundamental forces: gravitational force, electrostatic, which is what we're talking about here, and then nuclear strong force and nuclear weak force. Gravitational is the weakest, electrostatic is much stronger, and then the nuclear stuff we don't really experience because we don't live in nuclei. Yeah. No, it doesn't sound fragile. So how is water able to do that? And the answer is there's an energy exchange. When we talk about this in Chem 3B, we'll talk about how these interactions between the ion and the waters around them are a different kind of energy lowering interaction, but similar to this idea. No, ionic things are super strong. It's just water is amazing. Okay, so ions, sometimes you can see the charge and sometimes not. Here's a monatomic ion. I see the charge. Here's sodium sulfide. I can't see the charge. Here's a diatomic ion, mercury 1 ion. Mercury 1 travels in pairs because it isn't stable by itself. So this doesn't exist. This exists. And then when mercury 1 combines with something, a different ion, opposites attract. So this cation needs some anions, maybe iodide. The mercury 1 requires 2 iodides to balance that +2 charge. And then we have 1 polyatomic ion, that's ammonium. And when it's in a compound, we don't see the charges. But we still recognize that those are ions. Questions or comments? Okay, so ions, sometimes you can see the charge, sometimes you can't, but they always have charges and they stick together through electrostatic attraction like little magnets. Why is this important? You need to recognize that they have charge even when it isn't showing so that you understand why they behave how they behave, like in water. And at some point, you're going to need to understand how many pieces make up an ion so you can break it into pieces. For example, if I had something like this, sodium phosphate, I need to recognize that this 3 means 3 sodium ions came together to make that formula unit. And this 4 is just part of the chunk of charge that we call phosphate. So there's 2 kinds of subscripts here. The kind that mean 3 of these ions. And the other is, this means there's 4 of these atoms in this chunk of charge. So phosphate is an example of a covalent ion. Phosphorus and 4 oxygens are sharing electrons. I'm making a Lewis structure. But the chunk has gained 3 extra electrons. And so these 4 oxygens are covalently bound through sharing electrons, 2 electrons, to that phosphorus. That is a chunk like a water molecule, but because it has extra electrons, we call it a covalent ion or a polyatomic ion. So we are going to have to understand how many pieces an aqueous species breaks into when we do something called balancing equations, which happens in 2 weeks. Questions?
I have a question just about that specific bond. Are the 3 extra electrons just from the phosphorus? So the oxygen is basically happy sharing?
So phosphorus gave its 5 valence electrons and each oxygen gave it 6 valence electrons. And then they had to acquire 3 extra electrons to be stable to make that structure.
Okay.
Okay, so covalent are chunks of charge. And the chunks stay together. Anything that is covalent is sharing electrons, and we can draw a picture of it called a Lewis structure. And Lewisian structures are going to be important in Chem 3B. So we have to recognize ionic or covalent. Now we're going to practice. So the first thing to do is to decide, am I working with an element? How do I know? It would be only one capital, no charge showing. And if it's an element, we just name the element. Are any of these elements?
Chlorine.
Yep.
Yes, and we call it chlorine. How about the other one?
Phosphorus?
Mm-hmm. Okay, if it's an ion, there is going to be a charge showing if it's just an ion. I don't have any examples of, oh, I do have an example. There's an ion on this page. What's its name? There's one chunk of charge there. What's the name of that compound or that ionic, I'm sorry, covalent molecule, that polyatomic ion? Okay, it's one of the anchors that you need to memorize. If you haven't made flashcards, you just need to recognize carbonate when you see it. And it couldn't be more obvious because it's got its charge showing. Okay, and then for compounds, which is really kind of where we're headed. How do you know it's a compound? There's more than one capital and no charge showing. Then you need to decide if it's ionic or covalent. So for each of these compounds, decide ionic or covalent. How about this first one here?
Going to be covalent.
It is covalent, good. How about this one?
Covalent as well.
Covalent.
Yeah, how do you know?
Capitals.
Non-metals, good. How about this one? So boron is a metalloid. Metalloids share electrons. Covalent. How about this one?
Ionic,
How do you know?
because it has a metal.
Good. And this one?
Ionic as well, because of the aluminum.
Aluminum is a metal, good. Let's name those first because we learned how to name those last week. So I want you to think for a minute the names of those 2 ionic compounds.
Is that iron chloride?
It is an iron chloride. Which iron chloride?
Iron 2.
So iron is in the unknown zone. It could either be 0 as an element or 2 or 3. It has variable charge choice. Good. Iron 2 chloride. How about the other one?
Aluminum bromide.
Perfect. So you didn't say aluminum 3. How come?
Because aluminum is not a transition metal. That's kind of how I remember it.
Perfect. That works. Okay. So now for the compounds that are covalent. So if it's covalent, it's not made of ions. There are going to be 4 types. And so I'm going to quickly describe a thing that is it's in the video that's on the page that explains how to name covalent things. But I just want to give you a preview here. So there are the kinds that start with or are common names, like we just know water. So for common names in our class, there are 5. And water is one of them. And the extra credit has to do with a wrong name for water called dihydrogen monoxide. There is a site that talks about that. And I want you to go to the site and give me a factoid. The other ones you need to know are ammonia, which is super important. It's a very common covalent compound base. Usually bases are hydroxides like sodium hydroxide, potassium hydroxide are also called lye. But ammonia is a base. It's a weak base, it's important. And then there's methane, which is lab gas. That's what we burn in Bunsen burners. The 2 other ones I want you to know are phosphine and hydrazine. And I talk a little bit about those on the video. So over here, I do see one that has a common name. And that one is ammonia. Okay. And then there are the ones that are hydrogen containing, but they start with hydrogen. So besides water, there are some that just begin with hydrogen, and there are 6. Hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide, hydrogen sulfide, and hydrogen cyanide. There are only 6. So the hydrogen containing ones, which sounds funny because everything I've got up here for covalent has hydrogen, but the ones that start with hydrogen, these are gases. And when they're pure and a gas, we call them hydrogen block. But if those gases are bubbled through water, they can be named as acids. And so there's 3 kinds of acids. So these acids that are, these guys bubble through water, and their name changes. And then there are the acids that are made from ites and ates. So if you take nitrates and you add enough hydrogen ions so we have a molecule, at that charge, that's called nitric acid. And then if you had an ite, so now I might have nitrite, add enough hydrogen ions to make it a compound, and then hide the charge. That's nitrous acid. So if the anion was an ide, it makes a hydroic acid. And probably the most familiar is hydrochloric acid. That just sounds right. The ones that are made from ates, like nitrate, are ic acids. And the ones that are made from ites, like nitrite, are us acids. So those 6 hydrogen-containing compounds bubble through water, make hydroic acids, and then there are some other ones that are always acids. And then finally, there's the ones that students like the best, and those are the ones where you say, how many of each kind? And they're easy to say, like carbon dioxide. And we use Greek prefixes. We use mono on the second one sometimes, but mono, di, tri, tetra, penta, things like that, hexa. Okay, so here I have a covalent compound. How would you classify it according to that list I just gave you? H2CO3, what does that look like?
Hydrogen carbonate.
It does look like hydrogen carbonate. It looks like carbonate gained some hydrogens to make an ic acid. Eights make ic acids. This is carbonic acid.
Mm.
So I know it's an acid because it has oxygens. It can't be a gas. It's a covalent compound starting with H, carbonic acid. Okay, how about this one? BBr3. See, this is a how many of each kind. It's easy because it doesn't have any H's. Have you noticed that number 1, 2, and 3 here all have H's? But this one doesn't have any H's. So I'm going to say the first one is boron, the element name. The second one is bromine. For the second one, we give it an "ide" ending. And then we would say how many of each: mono, boron, tri-bromide, except we don't use mono on the first. So this is just boron tribromide. So that is your whirlwind tour of organic naming, but don't worry, it's laid out in more detail and slower, a little more systematically in the video that I provided for you. It also is in that packet, so I want to go show you the packet real quick. I'm going to go to modules and then last week's module. On last week's module, there was a page that said ions and ionic compounds. On that page was like how to predict main group ions and how to put compounds together. And then here there's a packet that says nomenclature. Sounds like it's lunchtime somewhere. Do you want to mute? Making me hungry. Okay, so this is the packet that we started last week, and there's some grids and some answer grids, and hopefully you've worked through that. And if you haven't, keep plugging away at it. It eventually things click, and then it's fun. Here's a page. So this is the practice that you should have done up through whatever page that is, 22. This page, naming acids, talks about the 3 kinds of acids. And then it gives you some practice. And I believe there's a key. So how to name acids is a page that has practice and answers, and you should probably do that. And then if you're naming covalent compounds, here's how to name the other ones. It talks about the common names you have to memorize. Rules 1 through 4 talk about how to use the prefixes and like when to drop mono and when to add ide. And then 5 is just talking about hydrogen containing, hydrogen fluoride, hydrogen bromide, hydrogen chloride. So all of this is contained in this packet. And then there's a practice page. And then there's answers to the practice page. Okay, and then hydrates, oh, for Chem A, you're in 3A. We are gonna do hydrates in Chem 3A. So just don't worry about them this week. But in 2 weeks, we'll have a lab and it'll focus on hydrates, and then we'll have a better picture of what that means. So that's not part of the nomenclature you need now. Then there's some practice pages and some keys. Okay, so that is the nomenclature packet that you had from last week. Now I want to go to this week. Let's see, here we are. So here's covalent nomenclature. That's the video that goes through just naming covalent species. And then here's for lab, 20 problems. Covalent nomenclature practice, number 1. And so this is the assignment that I suggested at the beginning that you do. And that you, after you've got all your answers, that you compare with friends. And then if you're not sure, you talk to me about. And I'm happy to help you with that. It is possible that at this point, an hour later, that this feels overwhelming. You don't have to say it, but if anybody wants to share that they're feeling a little overwhelmed, that would be fine. I think you're paying attention. But let me assure you, it is so doable. It just takes practice. And perfectionists, we're going to have to be okay with making mistakes because mistakes are part of learning. The time in your life when you learn the most, from 0 to 4, you made mistakes and you fell down all the time, but you always got back up.